Thanks for having me. I'm going to talk today about AI in healthcare. Just a quick resume for me. I did my PhD at Western University in London, Ontario. Graduated in '96, and then I was on faculty at Western as a postdoc and then faculty member for a couple of years before I moved to Calgary in 2000. So in 2000, I started at the University of Calgary in the Department of Radiology and the Faculty of Medicine. And I was there for 11 years, started a company which is still going. They make technology to read medical images on iPhones and web browsers that's sold around the world. In 2011, partly because of that software, I was recruited to go to Mayo Clinic in Arizona and start their division of medical imaging informatics. I was at Mayo for about 8.5 years, and then had the opportunity to go to Tampa, Florida, a big cancer center there called Moffitt Cancer Center, and become their first AI officer. And I was there for about 2.5 years or so before the opportunity to come back here and presented itself. So we actually moved in late 2021, in December of 2021, and we joked that we got on the plane in shorts and flip-flops and got off in parka and snow boots. And so people say, why on earth would you move from Tampa to Edmonton? People usually want to go the other way. And there's a bunch of reasons, but a lot of it comes down to Edmonton checking the boxes for addressing challenges for AI in health. So I found over the years that all those 4 large academic medical centers need a large university with a really strong computer science and engineering program. Mayo Clinic doesn't have that. They're not affiliated with the university. Tampa had the University of South Florida. They don't have a strong computer science program. It's good, but it's not like one of the top ones in the world. You need an AI hub with sort of an international, at least national, and hopefully international reach. Here in Edmonton, we have the Alberta Machine Intelligence Institute, one of the 3 institutes funded nationally by the Pan-Canadian AI strategy and through the Canadian Institute for Advanced Research, CFAR. And so they currently fund about 30 Canada CFAR AI chairs. I'm one, and there's a bunch of others. And they just recently announced, I guess it was a couple of months ago, they're expanding that to recruit 25 new Canada CFAR AI chairs. So that's 25 new faculty positions at the University of Alberta, all focused on AI. 5 of them will be in basic AI and computer science faculty positions, and 20 of them will be applied. 5 of those will be in healthcare. So we're going to get 5 new people like me here over the next year or so, which is phenomenal. So we're going to have about over 50 funded chairs. And the chair positions are really good. It's 5 years of salary support and 5 years of operating funds. And then the real kicker is population level health data. And this is something they don't have in the US. They have lots of large healthcare organizations, but there are heavy filters on the door. Like, look, for example, at Mayo Clinic. It's an extraordinary healthcare provider, and they see some of the rarest diseases in the world, but they're not population level, right? There's a heavy filter on the door. Not everybody in the US who wants to get treated at Mayo Clinic can. And so in Alberta, on the other hand, everybody here knows about the rollout of Connect Care. That's a product by a company called Epic. They're one of the 2 major healthcare electronic medical record vendors in the world. So Epic is deploying across the province. We will be the largest Epic installation in the world when the deployment is done. But even long before Epic, the people at Alberta Health Services in the analytics group realized that they needed to get all the data in one place just to help run the organization. So for 20 years, they've had a single integrated data warehouse in Alberta that's connected all these facilities, over 100 hospitals, 460 community-based care facilities, 17 cancer centers, and on, all connected and all depositing data into a single data warehouse every night. And so we've got 20 years of data on about 4.5 million people. And this just doesn't exist anywhere else in the world that I'm aware of, not even close. And it's true population level health. We have the Indigenous peoples in the north, we have urban people in Calgary and Edmonton, we've got farmers, we've got all different kinds of ethnicities. it's a fantastic data source for building models if you want to generalize them to other places and other populations. So I'm going to start with a brief introduction to AI. How many people here are familiar with neural networks? Heard of them? How many people know how a neuron in a neural network works? Okay, good. So we'll get into that. So AI, the term first appeared in 1956. This is kind of funny. They wrote two very famous AI people, one from MIT and one from Stanford, wrote a proposal to the Department of Defense to say, we want to hold a summer school to talk about this thing we're calling artificial intelligence. We're going to invite 4 or 5 people. When we pay for it, we think we can get AI all sorted out by the end of the summer. This was in 1956. Needless to say, not. But back then it was mainly rule-based systems, like if then else type statements. If you see this, do that. If you see this, do. And those were great when they work, but they're hard. It's hard to encompass all the complexity of the world in hard rules like that. And when you make changes, it has ripple effects through other rules in the system. So they become very brittle over time. But they work good for what they do well. In the 1980s, computer scientists started teaching algorithms to look for patterns in data. And those would then be correlated with something of interest. In healthcare, you might see a pattern in an image and correlate it with an outcome, like are they responding to treatment? And you would hand code the feature extractor. I spent a lot of time doing this in my graduate work and subsequently building image and signal processing algorithms to pull features out of images, and then using standard techniques like linear regression or other things as they were developed to correlate that with an outcome in the patient. Later, I mean, it started then, but really in the 2010s when portable gaming graphics cards or graphics cards that run in personal computers were starting to be used for doing scientific computation. They're massively parallel, and in order to run the game well, they have to be able to process billions of calculations in a second. And so smart people realized that they could use that power for other things besides gaming. So they started programming the cards to do matrix operations. They're really good at that because lighting in a game requires a lot of matrix calculations. And they realized that a lot of AI comes down to linear algebra. And so they programmed it on these gaming cards and got a massive speed up. And that's when deep learning really started to take off. And it's just machine learning, but you're using an array of artificial neurons to find the patterns, okay? So it's hierarchical. So what is this artificial neuron? Well, this is a schematic. We'll look at a neuron that has 2 inputs. They can have an arbitrary number of inputs, but 2 is pretty common. The 2 inputs, x1 and x2, are real numbers. They can be any value. And the neuron does something really simple. That's what we want it to do. The simple thing it does is it applies a weight to each input, which again is a real number, adds them up, tweaks the result, and if it's greater than 0, it passes it along. Otherwise, it just passes along 0. That's it. That's all it does, okay? So there are 3 parameters to learn, the 2 weights and the tweak, which is often called a bias value. That's what you learn. So that the network will start with random guessing, and it'll see how well did I predict the desired outputs. You've got a label that you're trying to predict in that particular sample. And based on the difference between your prediction and the real label, you use that delta to back propagate through the network and tweak these weights. And you do this millions and millions of times until the weights converge on a reasonable set of values to solve the problem you're interested in. I'll show you the demo in a second. But one cool thing about this theorem was just proved in 1989, relatively recently, in the scheme of mathematics, that these things can be used to approximate any continuous function to an arbitrary degree. So if we look at a network with a single layer of these neurons, and we have an input x and we're trying to predict the output y, and I've got an arbitrary function there on the right. I just made this function up. The essence of this theorem says that any pair of these neurons can be used to create a rectangular function. And the parameters, the weights and the tweaks, can be used to adjust the location, the height, and the width of this rectangle. So if I have 2, I can overlay this on top of the function, and it'll learn to adjust the height to minimize the error at that point. And every pair of neurons gives me another rectangle. And so with 10 neurons, I get 5 boxes, and we get an approximation to that function. It's not a great approximation to the function, but look what happens when I increase the number of neurons to 200, right? So a single layer, and if I have an infinite number of neurons in that layer, I can make the error infinitely small, okay? So with 200, I get a really good approximation, and that's just one layer. Now imagine I have multiple layers stacked up. You can see you can get some pretty complex nonlinear representation, all learned automatically. It's really cool. So I'm going to show you just before. So so the goal of this is a simple neural network with 2 inputs, X1 and X2, and we've got a orange cluster and a blue cluster, and the goal of the network is to learn to separate the two. And so with just one single neuron, you'll see that it learns very quickly to draw a line to separate the two, just automatically by adjusting the weights. And I can stop this and regenerate data, slightly different data, let it run, and see how quickly it learned to adjust that line. So with just a single neuron, you can learn a simple function like this essentially, right? No problem. Okay, let's give it something a little more difficult. This is a little tougher, right? You've got to draw a circle to separate the two. So let's see how it does with this. We set all the weights. You can see it's drawing a line, and that's about all it can do. It can't do much more than that. So we're going to add another neuron here. Run it again. And it turns out that with 2 neurons, you can get a graph. Essentially, is what you get. It's a graph that's almost able to separate the 2, but not quite. So I'm going to add a 3rd neuron, reset all the weights, let it run, and it learns very quickly to put a box around the cluster and separate the 2. Cool, it's done this automatically. No programming by me. I'm just adding neurons to a network. Okay, let's try this guy. Now here we've got 2 opposite corners. It's a checkerboard, so it needs to draw a checkerboard essentially. And it's done it instantly. Now what's interesting about this is I didn't reset the weights. I didn't do anything. I just loaded a new data set and said to go. And this demonstrates an interesting property of neural networks. It's called transfer learning. You train on one problem, and it can learn things that are applicable to a completely different domain. This is a related domain, but you can see the exact same network with the exact same weights solve this problem as well as the circle problem. So transfer learning is a big deal. And in medicine, an interesting application of this is one of the first applications was to train on a massive sample of hundreds of thousands of images from the internet of everything. Just pictures people had taken on holidays, so everything you can think of. And they trained a neural network to identify whether it's a car, a bus, an airplane, a dog, a cat, whatever. They had 1,000 different categories that these images were classified into by human experts. They trained the network to predict which of the 1,000 categories a particular image would fall into. People took those trained networks and applied them to MRI and CT scans, and they were able to predict things in MRI and CT scans, even though they'd never seen an MRI or CT. Right, so they learned something fundamental about images at a very low level that generalized into other domains. Really, totally unexpected until they tried it. So this is a pathological case that I studied when I was in grad school. You need a spiral to separate these two. They're 2 interwoven spirals. And this is a classic hard problem for clustering algorithms and trying to separate things. And if we run this on this, it just fails. It's still running. It's trying to learn, but it's really not able to get in. So let's add another neuron. Nope. Okay, max out all the ones in this layer. It's just not able to do it. Oh, yeah, I'm not going to believe this, but so you'll see here now it's starting to learn. So it took 2 layers of neurons, 8 in one and 6 in the other, and I will regenerate on the fly. And this helps it learn when you give it sets of data. If you let it run a bit longer, it'll converge on a pretty good solution usually. Anyways, this will run for a while, but you can see that 14 neurons. 14 neurons in 2 layers is capable of solving this problem. It'll solve it eventually. But usually it's done in about 1,000 iterations or up to 2,000 iterations of learning, but it will converge on a solution. See, it's partly there. So this is a much more complex problem, 14 neurons in 2 layers. And I'm going to show you something else. I'm going to add 2 new inputs. I'm just going to square the inputs. So no additional information. I'm just pre-processing the inputs. A simple pre-processing, I'm just squaring the values. Just like this. Done. And it's learned. It's done. Right? And it's a good solution. It's nice and smooth, and that will generalize to lots of other unseen spirals. So this tells you a couple of things. First of all, pre-processing is really important. And that requires domain expertise, right? It requires a computer scientist or a physician or somebody in your domain knows something about the data. That's critical. Architecture is important. You can't just throw endless neurons in a single layer. You have to design an architecture. That's important. And that's an art still, not a science. And the quality of the data that you give it is really important. So that's a brief demo of how these things work. And an interesting sort of footnote to this is a couple of scientists in Israel a few years ago said to themselves, they're neuroscientists, and they take human cortical neurons and blow them up outside the brain on plates, and they connect electrodes to them, and they give it inputs and they measure outputs. And they said, how many artificial neurons would it take to model a human neuron? Now, it depends is the answer. But in general, they found that it took 5 to 8 hidden layers and 1,000 or more artificial neurons to replicate one single human neuron, cortical neuron. And the human brain has about 86 billion. So you can see that just 86 trillion neurons isn't enough. You need at least that, right? But then the architecture is important, the data is important, the inputs are important, so many things are important. We have networks now that are this large. ChatGPT is 175 billion parameters, divide by 3 or 5 or something to get trained with neurons. So we're not far off having this many neurons in our artificial neural networks, but they're nowhere near human intelligence because of the architecture and the connections. And it'll be a while before we get there, I think. Okay, so with that background, introduction to AI, I'll talk about some applications of this technology in 3 areas. In medicine, text, drugs, and images. So language is hard for computers. Here's a sentence: the trophy did not fit in the suitcase because it was too small. So what does it refer to in this sentence? The suitcase. This is pretty simple. A young child learns this very quickly. Now I'm just changing a single word in this. In fact, the last word, because it was too large. Now what does it refer to? This is simple for us. We learn this right away, right? But to figure this out, you have to know something about things fitting in other things, and that's way outside the context of the sentence. You have to have knowledge about the world. You have to know something to be able to solve this arbitrarily. And that's really hard to give computers until some bright folks at Google described a new transformer architecture in 2018, and they learned to handle this on their own just by training. It's amazing. And a major problem in natural language processing for over 20 years, and this new architecture learned to solve it on its own. So this architecture was originally developed to translate between languages. And the first pair of languages was English and French. And the reason they chose that was because of the Canadian government. And everything that's said in Parliament is translated into both official languages at very high quality. So the guys at Google got hold of all that from the Canadian government and used it to train this. And so English to French translation is a solved task. It does it really well. So you have an encoder and a decoder. These are the two core components, and each of these is a vastly complex machine with many, many parameters, millions of parameters in each one. But we'll just look at it as a black box and closed machine. And so you take text as input, you process it. The encoder converts that stream of text into a numerical representation, and it does it in a context-aware fashion. So if you take a word like the word bank, there's not a single fixed representation of that word. It depends on the context. If you say, I went to the bank to get money out, or I cast my line into the riverbank, it has a different internal representation because the context is different. Okay, so that's a fundamental advance. So if we want to translate this sentence, I like French cheese, from English into French, we pass each word in, and it ripples through. The encoder takes that numerical representation, passes it to the decoder, and the decoder's job is to generate text in the new language. Okay, it's not ready yet. It doesn't have enough information to know. Obviously, it's just seen one word. So then it takes the output and sort of stores it, but does some additional processing. Then you pass I like in. You pass I like French. You pass I like French cheese. And finally, it sees the period that says, now it's time for me to generate some output. I think I'm ready, and produces the output in the different language, in the target language. So this is really good at this. And people quickly realize that they could build lots of other machines with the components, the encoders and the decoders. They're powerful machines in their own right. One of the first was called BERT. It stands for Bidirectional Encoder Representations from Transformers. That doesn't matter so much. The thing to remember is a lot of these models now are named after Sesame Street characters. So we have all kinds of Muppet architectures, but it's based on the encoder. That word encoder means that this new architecture is built up exclusively of encoders. Doesn't use any decoders at all. So what the heck are they doing with the encoders? BERT has 12 encoders in the base model and 110 million trainable parameters. Okay, so that's like 11 or 10 million parameters per encoder. So they're quite complex machines. Remember what we could solve with 14 neurons in 2 layers. Imagine this is many, many layers internally, and about 10 million parameters in each encoder, and they're all working together. And this thing is really good at looking for answers to questions in text. So here's a Wikipedia article. We're not going to read it. It's about the Normans. You can ask questions in this paragraph, like in which country is Normandy located? The BERT can learn, if you give it labels and give it examples, it will learn to find a continuous span of text to answer the question. France, in this case, when were the Normans in Normandy? The 10th and 11th centuries. Did they gain their separate identity? First half of the 10th century, and who was their leader? So if you give this a large set of question and answer, like a test, an exam on Wikipedia, it performs on par with an undergraduate student. Gets in the low 90s, 91, 92% correct, which is about the same as an undergraduate student. So this came out about 6 weeks before I arrived at Moffitt. And they said their number one priority was automatically extracting tumor site and histology from solid tumor pathology reports. They said, do you think you could do that? And I said, BERT. Just published, let's try that. And I spent 18 months building it. It was a lot of work. But I used a question and answer system, and I hard-coded 2 questions. What organ contains the tumor, and what's the histology? And it's more than just BERT, it's actually 3 of them. It extracts the text, passes it on to another BERT, which then maps that onto ICD codes. So you get ICD codes out. And on an unseen test set of just over 2,000 reports covering everything that a large cancer center in the US might see over a 50-year period. So it was 214 different sites on the human body and almost 200 different types of pathology for those tumors. Across that entire data set, it returns its top 5 predictions. Most of the time it's right, and the first one is correct, but it returns the top 5. In the correct answers in the top 5 between 93 and 96% of the time. So it's really good at reading these reports and returning the ICD code that corresponds to the disease. ChatGPT, everybody's heard about. GPT actually stands for Generative Pre-trained Transformer. It uses the transformers as well, but generative in this case refers to the decoder. You can think of that as a generator. It gets a numerical input and it generates text. And so ChatGPT is made up exclusively of generators. And the key thing here is the pre-training. What they do is they give it a sentence, like our familiar sentence, the trophy did not fit the suitcase because it was too, and they mask out that word and ask it to predict the next word in the sentence. And we know that this is arbitrary, right? It could be small or large, depending on what? Well, a lot of things. So how do you train this? Well, you feed this into a large neural model like ChatGPT, and it learns to make a prediction across its entire vocabulary. It has about 30 to 50,000 words in its vocabulary. And for every single one of them, it predicts the probability that that's the next word in the sequence. And if you pick the highest ranked one of those, let's say it's the word small, that would be what it would predict. Okay? If you do a greedy approach, let's just take the number one ranked. Sometimes you might return the top couple, like I did in my application. It depends. But in the simple case, you just return the highest ranked one. And so we put small in order to learn to do this, it needs a massive text corpus. And basically by massive, we mean every word that's ever been published digitally anywhere. The entire internet, the entire Wikipedia, you name it, if you've seen it, they grab everything that they can. The CEO of OpenAI said that, as an example, if you were a proficient reader, all you did for a living was read, and you did it for 8 to 10 hours a day, and you're really fast, this would see the equivalent of what you could read in 1,000 lifetimes. That's what they use to train ChatGPT. That's the size of the text. So it's everything you can think of. So when you hear things about like ChatGPT scoring really well in the medical examinations, that's because it's already seen them. We've already got the medical exams. It's trained on them. There's almost no text out there before 2021, when the training period ended, that it hasn't seen. Okay. And the other cool thing about this is it's 175 billion parameters. And you can think of those 175 billion parameters as space to store or compress the knowledge. So imagine how much text you can efficiently compress into 175 billion bytes of data, or even more, because each one is a large floating point number. So it's got enormous capacity to memorize its training data. This has implications for healthcare. We don't know how much of it's trained. If I train it on your electronic medical record, is it just memorized it? And if that trained model, which we think of as just a bunch of numbers, goes out beyond the hospital firewall, could somebody figure out how to retrieve your confidential information from the weights that have memorized the training data? So that answer is unknown. We don't know yet. But that's 530 times larger than the model I built that can read pathology reports and give ICD codes. Imagine what this thing's capable of. 530 times the size of something which is considered really difficult in pathology. Each training run costs tens of millions of dollars. So very few organizations can afford to do this, right? You know, Baidu, Google, Amazon, Microsoft, Apple is doing it internally. Nobody else can afford to do it. Research labs can't afford to train this. $10 million a run, and you need multiple runs to train it and tune it. And you need a $300 million computer to do the training in the first place. So it's just prohibitive. So what do you do if you want to use this in medicine? We refer to these things, I think typically over 7 billion parameters now is what we call a large language model, but we're up into the 175 billion. Nobody really knows how big GPT-4 is because they haven't released it. They're keeping that under wraps, but it's probably even bigger than this. Probably not a lot bigger because architecture matters and training matters, but probably, I would say at least double. So what do you do if you have sensitive data that you don't want to send up to OpenAI and ChatGPT because it might memorize it? Well, in July this year, Meta, Facebook, released a model called Llama 2. And Llama stands for Large Language Model for Meta AI. This is the second version of it. The first version was closed source, but the weights got leaked. Somebody posted the weights on the dark net and it spread like wildfire. And once the genie is out of the bottle or out of the lamp, you can't put it back in. And so the whole world took off and people were running this on their local computers, on big computers. And the amount of innovation that took place in the following 3 months was, the guys at Google wrote a paper that's famous about it. It was an internal memo that said, we have no moat. The moat was that we're the only people who can train these models. And now that the weights got out, everybody was tuning them and training them and making smaller versions of it. And then basically they said that our roadmap for the next 10 years was basically accomplished by the open source community in 3 months. Right? It's just they're just phenomenal innovation between July and continuing to now. So Llama said, okay, or Meta said, oh, they're using our model. At first, Meta said, give us our weights back. People just laughed. And Meta said, okay, well, everybody's training on our model, and we have the right to use those advances because it's part of our license agreement. So they said, heck, let's just fuel the fire. So the next version they released completely open source for research and commercialization, provided you have fewer than 1 billion customers, right? So they don't want their direct competitors like Twitter and LinkedIn using this model. But if you have less than 1 billion customers, you can use this for commercialization, and research is all known. And they have red teams. They call them red teams, and they get early access to the model. They try and get the model to do bad things, like produce biased output, tell you how to make an atomic bomb, those sorts of things. And then they train that out of the model. So they are very active, very aware of this, and it's ongoing. And then they blind test it. So they'd have ChatGPT answer a set of questions, and they'd have Llama 2 answer a set of questions, and have people judge which is better without knowing who generated the answer. And about 2/3 of the time, they said that Llama 2 was on par or better than ChatGPT. So they're roughly, but it's only 70 billion parameters. I say only because we're comparing it to 175 billion parameter model. So this shows the power of data and the power of architecture. It's less than half the size, but it performs on par. And to run this requires 1/4 of one of these servers. And we have one of these installed at the University of Alberta behind the firewall in a facility called DARC. It stands for Digital Analytics Research Group. And we're in the process, hopefully just a few weeks away from getting what's called an information management agreement with Alberta Health Services. And that they are the custodian of protected health data. And if we get this legal agreement signed, we will be legally able, we meet all the security criteria, and we have a contract in place that will allow us to put confidential patient information on this server. And now we can train with Llama on confidential patient information to do all kinds of things for healthcare. And that's what I'm trying to do. So the first thing I did was build a playground to allow people to tune prompts on their own data. And the way it works is you play with prompts, you type in a question like, what's the patient's age? What's the patient's gender? What's their major condition that they're in being seen for? And it'll read that medical note and try and produce an answer. Once you've tuned up the prompt and it looks pretty good, maybe on 100 cases or so, you can then say, okay, now apply this to the rest of my data. It'll go off and use the whole machine in parallel, produce an Excel spreadsheet with columns as output, and put it on a secure drive and send you a link. And then you can get this link, and now you processed your entire data set. So all kinds of clinicians throughout healthcare have really interesting data sets that they spend decades sometimes labeling. And they're always trying to find things in clinical notes. They call it a chart review. They send med students out to read the chart and pull things out. We want to make this process highly automated, and we want to make it available to all the clinicians in Alberta at any time. Not there yet, but that's the goal. They don't need a programmer. That's the key. Get powerful tools in the hands of smart, ethical people, and good things will happen. So the first example of this is detecting pulmonary embolisms in chest CTs from radiology reports. And how many people here know what a pulmonary embolism is? Most people do. Well, okay, I'll skip over this. It's a clot that forms typically in the veins of the leg when you're not walking around on the airplane and not wearing your compression stockings. And when you get up and move, that clot flows up into the heart and out into the lungs. It clogs one of the major arteries in the lung, and you have a lung attack, like a heart attack, but with a lung leaking. It's serious. And the best way to detect it is to order a chest CT scan. And they do this, and the radiologist gets told it's stat. They have to drop what they're doing, do this, and read it and report right away. It's urgent. So the question is, we're not trying to diagnose here. It's quality. It's a retrospective review of quality. And it's a critical test, but it's an expensive test. So it's worth trying to optimize it. And that's what Jake is trying to do. He's an ER doc. Are we ordering too many, too few, or just the right number? And can we determine this per physician person? So he came to me and said, we need a way to read these reports at scale. He's got a medical student who's labeled 10,000 of these reports. difference. Okay, and the labels are positive, negative, or indeterminate. There's not nothing in the radiology report. Actually, often they say we don't know. And so I took these and trained on 100 using my prompt playground and ran it on 1,000 and gave the output back to the med students. And they pointed out a bunch of errors that my model had made. There are things, oh no, this is considered a PE, it's a different term for it. So then I went through a second round of tuning on that 1,000, and then finally I ran it on a completely unseen, further 1,000, unseen by me. So I'm going to ask you to play medical student for 2 reports. And this is the report in its entirety as we get it from the radiologist. Point number 1, no pulmonary embolism. That's a key. That's a hint. Remember that. Number 2, mild pulmonary edema and blah, 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 a bunch of other stuff. So the med student can say positive, negative, or unknown. How many people think this is positive for a pulmonary embolism? How many people think it's negative for a pulmonary embolism? Okay, and how many people think it's unknown? Not that you're unsure, but that the radiologist says it's unknown. So lots you didn't answer, but some people, okay. So the med student here actually said positive, which is wrong. This is a case where it's negative. Okay, it's clearly negative, point number 1, right? So Llama 2 running on dark behind the firewall said it was negative, but I don't just ask it to make a prediction. I say, explain yourself. What's the rationale? And so it generated this as well. And it says the clinical note does not mention any conditions listed. There's a bunch of things in the logs because those conditions can occur elsewhere. The note specifically states no pulmonary embolism at point 1, and the rest of the note describes other findings unrelated to these conditions. So this is Llama 2 without any tuning. I just pulled it down off of the public domain site and done some prompt tuning, and it can read this note and produce this rationale for its prediction, which is really cool. And the output spreadsheet includes a column, which is the explanation, the rationale. It gives you the negative and it gives you the explanation of all of the cases. Case number 2, very limited study due to patient compliance, best images possible, no definite central pulmonary emboli are seen, small segmental or subsegmental emboli difficult to exclude due to the limits of the scan. And then they go on and talk about other things that they should be worried about in this patient, which radiologists are required to do by law. How many people think that this is positive for P? Nobody. How many people think it's negative for P? Remember, no definite central pulmonary emboli are seen. That's a clue. How many people think it's negative for a P? Nobody. How many people think it's unknown for P? Most people think it's unknown. That's cool. So the med student said it was negative, but the model said unknown. He gave this explanation. Clinical note states no definite central pulmonary emboli, but small segmental and subsegmental are difficult to eliminate because of the scan. This indicates the presence of PE and other related conditions cannot be definitively confirmed or ruled out. Therefore, the answers are known, and that's the correct answer. So I didn't write that paragraph. It wrote the paragraph. Can you wait to the end for your questions? We'll get you questions. Thanks. And the cool thing about this is, I'll talk about it in a minute. So this is the 1,000 that I haven't seen and the model hasn't seen, no prompting, right? And I got it to go through, and I have the labels from the med student, and the model agreed with the med student on 982 of the 1,000, which is really good off the top. But we're going to assume for now that those are all correct. There'll be some where they're both wrong, but to figure those out, we have to do a consensus read, and that's underway. So for the time being, we'll assume that 902 are mostly correct. I was interested in the 18 where the model disagreed with the med student. So I went through those myself, and I determined that the med student was right on 3, the model's right on 13, and they were both wrong on 2. Okay. So what that means is the model either agrees with the human or produces a different but correct answer 99.5% of the time. And it does 150 milliseconds per report to read it, make the prediction, and write the paragraph explaining how to make this prediction. This is better than a human. Jake saw this and said, this is phenomenal. This will revolutionize the process of chart review in medicine. Once you take, and we didn't have to do any tuning. This is just playing with prompts. I can take this further. I can tune the model on specific data sets, and I can do something called retrieval augmented generation. I won't get into it, but it's another step towards fine-tuning the model for a specific use case. So we've got a lot of room to make these models more powerful. This is off-the-shelf model with a little bit of prompt tuning by me, and it's performing better at reading these reports than a med student. Imagine what this is going to do. Okay, it's pretty cool. So one of the other things I've been interested in for a long time is what's called an AI scribe, AI-assisted documentation. So an AI agent listens to the conversation between the patient, provider, and the patient. And when they're done the conversation, the note is generated. That's the goal. The technology exists now, so I built it. It took me about 2 weeks to build this. And to build this, I didn't want to use Alberta data, so I went out and looked. And sure enough, about a year ago, some folks in Ontario published a data set in a good journal of simulated conversations between the patient and the provider. This is what they sound. They had 272. This is what it sounds like.
What brings you in here today?
Yeah, I've just been feeling breathless and it's getting worse. So I wanted to check it out.
Okay, and when did you first start feeling breathless?
About 2 months ago.
Okay.
So I'm just going to pause it. It's about a 12-minute conversation. So I took one model, open source model, and this model is really good at, it identifies the language being spoken automatically. It converts the audio to text, identifies the speakers, labels each speaker, and then aligns the text with the voice. So this is what you get as output.
What brings you in here today?
Yeah, I've just been feeling breathless and it's getting worse. So I wanted to check it out.
Okay, and when did you first start feeling breathless?
About 2 months ago.
Okay, and did it come on about like gradually through time or suddenly just happened?
I guess gradually, yeah.
Okay. And do you feel, how often do you feel breathless?
I'd say it's worse when I walk more than 50 meters. That's kind of the main trigger, just exertion.
Okay, and were you able to walk normally more than 50 meters before 2 months?
Yeah, 3 months ago I was fine.
Again, it goes on, but so this is the transcript that I get as output, parts labeled, and I take this and pass it into Llama 2, and I say, please summarize this this transcript and highlight any important clinical information and list any medications that the patient is on that are mentioned in the conversation. This is the end where we got to. 2 months ago, I was fine, and you can see that this goes on for a bit. That's not even all of it. So after it's done the summarization, this is literally the output we get for this case. And if you read this and read the transcript, this is a good note. It's quite a good note. And what's neat about this is the 12-minute recording to get the transcript and the note took 22 seconds. So by the time you're done the conversation with the patient, this note could be ready for you to paste into Connect Care. Okay. And in fact, a colleague that we're working with, he's an ER doc in Red Deer. ER is a very tough situation because it's every kind of medical condition you can imagine, and it's a chaotic, loud, and noisy environment. He's been running this for 4 months in Red Deer, and he's been collecting data on it, on his own performance. So it's an N of 1, but it's a start. And so far, he has shown that his productivity is increased by 20% by using this tool. That translates into 3 additional patients seen per shift, or 1 hour of saved time per shift, which is really cool, right? We're talking about unclogging ERs with this tool, but most important to him is his quality of life has improved dramatically. He loves this tool, and all his colleagues in Red Deer now want to use it. And the way he's got it set up, he brings his laptop in, asks the patient, do you mind if I record the conversation? They uniformly say yes. He clicks a record button on the screen, and when he's done, he clicks stop, and he waits the 25 seconds or so, and he copies that and pastes it into Connect Care. So it's not integrated, right? We can do a lot better by integrating it into Connect Care, but at least for this prototype, it's a copy and paste. And he's learned things. Like when he first started doing it, he edits the note that comes back. And he noticed a couple on, fairly often that he's like, I don't think we talked about that. So you go back to the patient and say, did we talk about this? And the patient says, yeah, we did. And he said he realized the note was better than he was at remembering the conversation immediately. So imagine if you're a doc and you're trying to do the note at night after you put the kids to bed and you saw the patient at 8 o'clock in the morning, right? How much are you going to remember? And the other thing he learned very quickly was when he's examining the patient, doing the physical exam, he calls out things to the AI scribe and tells it things that then appear in the note. And that helps him with his documentation immensely. So he says faster and better notes, much better quality of life, increased productivity. This is something that clearly has to come to every physician in the province of Alberta, right, to reduce their documentation. Imagine if we could save every physician in the province 1 hour per day by doing this and increase the quality of their life and reduce the chance of burnout. What kind of an economic impact would that have on the healthcare system? We've got about 12,000 physicians that work for IHS. We're not, because it's so compelling, we obviously are not the only people working on this. The big guys are in it, and there's several small startups across Canada that are working on this as well. Oracle bought Cerner, one of the the main competitor to Epic. And Epic has made a deal with Nuance, which is owned by Microsoft, which effectively owns OpenAI, which has GPT-4. So that whole thing is coming to Epic, right? This is coming to Epic for sure. This is coming to Alberta, but at what cost? I've heard estimates of $1,500 per seat per physician per month, which would work out to about $150 million a year for IHS to get this technology into Epic. Not cheap. Could be good value, but it's not cheap. Our system costs tens of dollars a month per seat. So about 2 orders of magnitude less expensive. Is it worth it? I don't know. There's a value proposition determined, which we're not, you guys are good at that, we're not. What we can contribute, it's not that, like, if I built this in 2 weeks, anybody can build it. There's no technical barriers anymore to this. There's integration, which is key. Cut and paste is not desirable. But there's validation. If you look behind the scenes, you find out that Epic and Oracle still have humans in the loop because they're worried about the legal ramifications. But we also have data from patient-provider interviews. We have human-generated transcripts, and we have expert-generated summaries of those transcripts. But we don't have 272. We have just over 1 million. And these are on the dark server right now. So this could be very valuable to a company like Cerner or Epic or Nuance if they want to validate their tools. So that's what we're going to do. We're going to do some work on this and publish it, and then go and approach these companies and say, would you like us to validate it in the Alberta context? Drug development, 2 more minutes left. So this fellow won the Nobel Prize in 1972 in chemistry, and he worked on RNA. And he said, you know what, we should be able to predict the structure of a protein given its linear amino acid sequence in the genome. And that kicked off a grand challenge in structural biology that's existed ever since. And here's an example of amino acids, and it turns out they form protein hemoglobin, pretty important protein. So how do you use transformers for this? Well, instead of taking a sequence of words, you take a linear sequence of amino acids. And the bright folks at DeepMind, soon after the transformer was published, they said, they've been working on this problem already. And they said, we can use this new technology to try and tackle the problem of protein. And so they did. And in 2020, they entered the semi or biannual big competition where they take all the known proteins, and you can train on that. So you know the amino acid sequence and you know the final structure. There's lots of those out there. But there's new ones that are figured out each year, and those are sequestered and held by the competition organizers, and those are the ones that you test against. And so every 2 years, they have enough new ones to run this test. So in July 2021, they open sourced this, the second version of it, and their predictions for every protein in the human proteome, 20,000 proteins, and put it on a database run by the European Bioinformatics Institute. And you can just go and look them up. Go in and search for a protein and find its predicted structure. And for that, they got the method of the year on Nature Methods, and the editors in their editorial said, these approaches have sent shockwaves through the structural biology community. We anticipate far-reaching and long-lasting impact, which I take as code for, it turns out the way we think, they're going to win the Nobel Prize in Medicine for this work. And then just over a year ago, they released predictions for every protein known to science, 200 million proteins, and up in this database. And what's cool about this is just last week, John Jumper, the lead scientist, was here in Edmonton. He'd been awarded the Gardner International Prize. 1/4 of those winners go on to win the Nobel Prize in Medicine. So he's on his way. And so I got to meet him, got to go over dinner. It was really cool to talk to him about this. So the last thing quickly I'm going to talk about is images. And to do images, you just break the image up into serial chunks and feed them through the transformer. You wouldn't think it would work because images are 2D, but it works. It's amazing. This is this transfer learning thing, right? Where developed from one domain and applied to another. Our primary application right now is inflammatory bowel disease, and they don't have a metric for the degree of activity. They know if you're active or if you're in remission, but that's about it. And a binary status isn't great when you're trying to measure the effect of treatment. So what they really need in this field, according to the gastroenterologist, is some way of quantifying the inflammation in the gut. And it's just too exhaustive. It's just impossible for to do this during an endoscopy or to do it retrospectively looking at a CT scan because the organ is huge and it's complex. And so we actually have a data set. This is not the entire data set. It's a subset of those that have imaging, just over 58,000 patients, imaged over a decade, almost 3 imaging studies per patient for a total of 160,000 abdominal CT scans. This data is on dark right now. And so our goal is to use deep learning to extract the tube, as I tell my students. We want to pull the tube out, lay it out straight, and then measure the inflammation from one end to the other, come up with an estimate. Then we would be able to tell the physician the degree of activity, the degree of disease of the patient. And so I'll skip over this. I take in the input images. I feed them into this machine that we have, the deep learning supercomputer, and it extracts the tube. And to do this, I use an open source tool, a couple open source tools. When you do this on like 10 or 15 or 100, it's a very different process than when you do it on 10,000 or 100,000, right? When you start to scale things up, everything changes. And so I built a pipeline and I tested it early this year, and it did just over 1,000 exams in 4 hours, which works out to about 14 seconds per exam. That sounds fast, but if we had to do our entire data set, it would take a month, running this thing full time for a month. I'm not the only person using it. This is for the whole faculty of medicine, right? And the reason we did 1,090, kind of a weird number, is because I actually filled the hard drive on this supercomputer and my program crashed because I had no more space to write. So for me to process our data, to train the transformer, just to hold the data, I need 160,000 times more storage. And we don't have that, right? And we need a better computer to do the processing as well. That would help. We could do it on this, but nobody could do anything for a month for research. One of the components of my pipeline is an open source program called Total Segmentator, created by a group in Switzerland. And it automatically segments over 100 structures in abdominal CT scans. And here's a look at what they are. And you can see the GI tract is one of the structures. So that's the baseline. I use that to pull it out. Does other things as well. And this is one of our patients. This is a Crohn's patient here in Alberta, and I've applied Total Segmentator to segment over 100 structures in their gut. And it's beautiful. It's done a really nice job. You can see the liver there in red, see the 3D rendering. Scroll through this and look at all the organs. And this is cool in its own right. What I would like to do is apply this to all the CT scans in the data warehouse that have ever been acquired over the entire history of Alberta, back to when the data warehouse was created, and every new CT scan that's ever acquired in the province. Segment them and store these masks in the data warehouse so that anybody going forward can just know that they have the entire body segmented. If you need to know, you're a nephrologist, and you want to know if your patient's kidney volume changed over time, it's now trivial to get that. Today, it's impossible. They have no idea. But it goes from being impossible to trivial. That's the goal for every organ in the human abdomen. But it's not perfect. And they admit this. And they say the hardest thing that they have, their system is least accurate on the intestinal tract. And so this is the output from that deep learning system, and it has some errors. So I built a labeling system, which is like, uses other open source components to allow us to correct these. And once they're corrected by an expert, we'll use this to train the definitive model. And to make this scale, I got it running on Amazon, AWS, Amazon Web Services. And right today, it's running on the Canada Central Node in Montreal, and it's running in Frankfurt for some German collaborators. And this is what it looks like. It uses a worklist manager, so you just say next, previous, next, previous. It does all the loading, the saving, it does everything so that the doc doesn't have to know anything. You just fire this up and you next, 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 next. And then what comes up is an open source program, which is like Photoshop, but for 3D medical images. It lets you correct things. It's built-in algorithms. So that is controlled. And the whole thing runs in a browser on a virtual machine in the cloud provided by Amazon. So you can go through and correct things. I'll skip all this. And so, like I said, once we get the corrected, we're in the process now of validating this, some internal validation with some med students here at the University of Alberta. Then we're going to release, get some radiologists here to play with it. And once we're confident that we've got a smooth enough, sophisticated enough system, we're going to start recruiting radiologists at the big GI conferences international, which is why I have it running on Amazon. So if we get people in Australia or in China or Japan, I can just pop this up on a node there and they will get good interactivity. What you saw in that video was me in Edmonton and the software running in Montreal, and it was really good interactivity. So Amazon's really got that worked out. And then we want to open source this so that anybody in the world can use it for labeling anything. If they base it off that total segmentator, they just have to change a text file. Like I literally put in a text file, I want the esophagus, small colon, the large colon, and the stomach, and it does everything and just is ready to go. So someone could set up a kidney segmentation or a liver segmentation trivial. So that's the goal. So what's the significance of it? Well, just last year, September 2022, just over a year ago, Chan Zuckerberg announced a big grant, UK Biobank, to create the world's largest imaging data set to understand disease. But what they want to do is enroll 60,000 participants and convince them to get a second abdominal CT scan. They already have one as members of the biobank. They've agreed to have a baseline abdominal CTs. They've already got that. So they want to get 60,000 to undergo a second scan, and they'll have 120,000 total. Does sound familiar? I've got 160,000 abdominal CT scans on dark right now, okay? Just for IBD patients. Over a 10-year period, almost 3 scans each. They figure it'll take them 5 years to finish collecting this data. And to do this, it's got lots of applications, but they required almost $50 million to acquire this data set, which is smaller than what we already have on dark. And our data set is just IBD. This is all diseases, right? If we did all diseases in Alberta, I don't know how big the data set would be. It's just crazy. But I can't even process them, right? I fill the system up. And for me to buy the hardware that I would need just to process this data set would be about $1 million. And then I need people and software and things like that. So I'm trying to convince the university to phone up Chan Zuckerberg and say, hey guys, we heard it, but in 5 years, we're gonna have a lot more than 120,000 scans just for IBD. How about you give us 50 mil and then we'll clean this and make it a public data set as well. So that's it. That's everything that I'm talking about in this talk. And I'll leave you with this final thought. This is Sam Altman, the CEO of OpenAI, creator of ChatGPT and GPT-4. And he says, as hyped as AI is, he still thinks it's underhyped. And I think this is particularly true in medicine. This is going to have just the AI scribe alone could revolutionize throughput in our ERs in Alberta. Imagine if every ER physician in Alberta could become 20% more efficient. right? And we could do this at a cost of tens of dollars per seat per physician per month. We should just do this. We should just build it. The tech, we've got it. What we need is to scale it up. We need the hardware to deliver it. It's not a technical burden. It's an implementation issue and a cost issue. Imagine the savings. So you think the politicians, imagine if any government could say, look, we just reduced wait times by 20% or more across the province in the ER. That'd be good. So happy to take questions. Thank you.
Thank you for all the good work you're doing in this field, and I was glad you touched on the parts of the data. I was wondering for the assisted documentation, considering Canada's diverse population, how do we approach generating long outputs for patients or doctors with different accents? How are we doing this?
Yeah, so I've had that question before. I have a supplementary video here. Can I have time to play it?
Yeah, for online, it might be good to repeat the question, just.
Yes.
Yeah.
So the question is about privacy and diversity. What do we do about patients from diverse backgrounds and physicians from diverse backgrounds who may, for example, have an accent when they're speaking English? Is that a reasonable summary? And it's an absolutely paramount question. I almost always get asked that one first for good reason. It's a very valid question. And the answer, it's not solved yet, but I believe it will be. And this is part of the reason why. So I have this running on dark. I downloaded it and I have it running on dark. It's limited right now. It can only handle about maybe 30 to 60 seconds of input, but it's version 1. And they will continue to produce things. Now, this doesn't solve the problem directly, but you can see where they're going with these language models. It'll be able to understand anybody speaking any language. And what's cool is translate. Suppose you're interacting with a patient whose native language is in English. You could potentially have them speak, say, Vietnamese, and you speak English, and this thing is translating in real time. And then at the end, you have put your note in English and connect here, but it produces a Vietnamese note for the patient to take home. Right? So there's all kinds of possibilities coming. So it's not solved yet, but I'm very hopeful that new technology that we don't have to build. Now we could help, right? Like I bet they have no indigenous languages in this model. I bet there's 0, right? We could, in Alberta, we could help with indigenous languages or other things, right? So there's all sorts of possibilities for us to collaborate.
Just a couple of quick things. Well, I think it's really exciting, and thank you for the presentation. It's really, I understand things better now. 2 quick things. One is provider resistance. Yep. I think because there's a lot of basic performance reporting back from physicians often is resistant. So that's just one quick question. Yep. And the other one is following the money. Because I'm just wondering, sometimes there's concerns of, say, the U of A or university professors, U of A, who is perhaps happening, who's getting money, what's the relationship with industries, and how we can get trapped in advancing this forward because of commercial interests wanting to own certain segments of the pie in competition. So just those 2 things.
Sure. So one is pushback from physicians. And in my experience at Mayo, especially at Mayo, it's all about trust. You have to build trust. And so you need to put guardrails on things, but fundamentally you work with the provider. So my appointment is in faculty of medicine, and that was a condition of me coming here. I didn't want to be in computer science. Affiliated with them, grad students, all that stuff. I don't want to build a hammer and go looking for a nail, right? The physicians come to us and say, we have this problem in our clinic. If you could solve this. So example, I'm working with a rheumatologist, and they get letters from primary care physicians saying, please take my patient into your rheumatology clinic. Here's why. And it's a couple pages. And I think there's 4 of them in the clinic, and they spend over 600 hours a year reading these letters to extract things, to triage the patients. And she said, do you think you could help? And I said, probably. Now, we won't get rid of 600 hours, but imagine if we get each of them back 25, 30, 40 hours a year, they can shorten the queue, right? They're coming to us with the problem, and so we will help them. It has to go from grassroots. And also, the IT and the higher ups at Alberta Health Services just don't want to spend more money on anything, right? But if a physician comes to them and says, look, I can see 3 more ER patients a shift if you spend money on this, and that translates into this amount of saving, then you can convince the leaders to make that investment. So that's how we did it at Mayo Clinic, and we're on that path at Moffitt as well, is to have the applications driven by me in the clinic. So then the second thing is, what about commercialization? And so, very valid question. My belief, and I think it's pretty common throughout Alberta Health Services and the university, is that anything that we develop that uses Alberta patient data is the property of Alberta. And by that, I mean Alberta Health Services, because they're the custodian of the data. So I've told them, and I said, I'll sign anything you want. Any model that I train, you own. I'm not going to go off and commercialize it unless you are a co-owner of that technology. And any revenue that comes back in, it could be whatever, increase in stock value. Like, suppose we do something really cool for Epic. Well, Alberta AHS should be able to turn around to Epic and say, okay, now give us a cut on the annual cost of deploying Epic across the province. If we train a model and Epic goes and sells that in a bunch of different jurisdictions, that should reduce the cost of running Epic in Alberta, or something else should come out of that. So I've told them a million times, first of all, no model, you're a co-owner. That's critical. So no model leaves the firewall without your permission, without appropriate safeguards. And I'm a little leery about training models for industry on our data because of the ability of these large models to memorize. So I haven't sorted that one out yet. It'll come when scientists have done more work on how do we ensure that memorization isn't happening. I believe it might take 5 or 10 years, but it'll come. And we need to be ready for that. But in the meantime, I'm consulting with the Cancer Center and with the AHS and telling them, be wary of these large language models. They can memorize a lot of stuff. So you just have to be careful about that.